Okay, welcome back. We are still busy with example 52. We want to solve this linear programming problem. In the previous lecture, we used the constraints to find the feasible region, and now we would like to find the optimal solution for x1 and x2 so that we can maximize our objective function. So if you look at this graph here, this is the feasible region, and the numbers are the three constraints. So I've got constraints 1, 2, and 3, and the shaded red shaded area is my feasible region. So I know that my solution must fall within this feasible region. So now to find the values for x1 and x2 so as to maximize my objective function, I'll start by drawing level lines. Now, a level line would be when you take your objective function and set it equal to any arbitrary constant. You will see there in your notes, if you set your objective function equal to 16,000, so let's just do that. Then we want to draw this level line on our graph. Now, I'm not going to go through the whole detail, but we go about exactly like we've done to draw or to plot any linear function. So the 2 points that you can connect will be where x1 is 0 and x2 is 8, and the point where x1 is 10 and x2 is 0. Okay, so that is one of my level lines, and we can draw another level line. If we look at the notes, we could set our objective function equal to 22,000. Okay, and again, 2 points that will lie on this line are the points where x1 is 0 and x2 is 11, and where x1 is 13.75 and x2 equal to 0. So we can draw this level line on our graph as well. Okay, so as we said, these lines are called level lines, and any point at a level line secures the same value of the objective function as any other point on the same line. So any point on this first line will secure a value for the objective function of 16,000, and any point on the second level line will secure a value of the objective function of 22,000 rands. However, the level line, the second level line, does not contain any feasible points, and we know that the solution must lie within the feasible region. So to find the values for x1 and x2 to maximize my objective function, we will start by drawing a level line, and then if we want to maximize, we will keep the same slope and then move our level line through our feasible region in an upward direction. And that is if we want to maximize, which is the case for this example. If we would like to minimize, you will move your level line, keeping the same slope, through your feasible region in a downward direction. Now, if you move it in an upward direction, then you will find your optimal values for x1 and x2 at the point where your level line exits the feasible region, the very last point where your level line will exit the feasible region. So if we take this level line here, this first yellow line, and we move it in an upward direction through my feasible region, then the very last point where this level line will exit my feasible region is at this point here. Let's call it point A, that corner point, exactly at that corner point there. And that is where we will find the optimal value for x1 and x2. Now, how do we find the value of x1 and x2? We do that by setting my two restrictions 1 and 3 equal. Why is that? Because point A is at the point where these two restrictions intersect. So to find x1 and x2 at point A, we will set restrictions 1 and 3 equal. So we can do it on the next slide. Okay, so restriction 1. That's my restriction 1. And my restriction 2 is x2 equal to 8. Now, it's easy to solve for x1 and x2 in this case because we already have the value of x2 that's equal to 8. So to find the value of x1, I can just substitute my x2 with an 8. So I still need to find the value of x1. I substitute my x2 with an 8 because that's given, that's restriction 2. Okay, so 8,000 x1 will be 100,000 minus 72,000. And if you solve for that, you get that your x1 is equal to 3.5. Okay, so now we know that my objective function this objective function subject to these constraints will have a maximum at the point where x1 is 3.5 and x2 is 8. And if we want to know what this maximum value is, we will just substitute my x1 and my x2. So I know that my x1 3.5, x2 8 will maximize my objective function. So to find the maximum of this objective function, I will substitute my x1 with 3.5 and my x2 I will substitute with 8. And that maximum is then equal to 21,600. Okay, just a few important observations here. The graphical methods are only applicable if the linear programming problem has only two decision variables, because we have to work in a two-dimensional space. This rarely happens in practical applications, so it's not very realistic. The level lines are parallel lines. The optimal point will always be found in a corner point of the feasible region or the solution space. If you go back to our graph here, the red is our feasible region and our solution lay at one of the corner points. We have, for this one, we have 1, 2, 3, 4, 5 corner points, and the solution lay at point A. The solution will always fall at one of the corner points. And this is true for any linear programming problem, regardless of the number of variables or constraints. And this fact creates the foundation for solving any LP problem.